All right, here's one. Limit as x goes to a, all right, of 1 over x minus 1 over a, all divided by x minus a. And, okay, so we're assuming a is not equal to 0. So what's the trouble here? You got 0 upstairs, you got 0 downstairs, right? Type 0 over 0 again. So what do we do? What can we do upstairs? We can make a common denominator, right? So like, I'm going to rewrite this as 1 over x minus a times the numerator. So the numerator is what? It is a minus x over xa, or ax if you like. So what I've done is I've written the numerator as, I'll scribble some stuff in here. So you multiply this by a over a, right? Multiply this by x over x. And then you combine those, that gives you a minus x over ax. So all of this is this right here. And then the 1 over x minus a I just kept out there, all right? Now what happens? What happens with this guy and this guy? They're not quite the same, but they're just, what? They're negatives of each other, right? I can factor a minus out. So this simplifies to the limit as x goes to a of minus 1 over ax. At this point, we have an expression continuous at the limit point. We can just plug in x equals to a. What do we get? Minus 1 over a times a, which is a squared. So there you have it. I'll make these easier. The limit as x goes to pi of the tangent of the sine of x. And this one, I'll make the limit as x goes to 7 of the exponential of x squared minus 49. You definitely don't need as much white space as I've devoted for these. All right. So here's how it goes. This is the tangent of the sine of pi. What is the sine of pi? It's 0. What's the tangent of 0? It's what? What? It's 0, right? Yeah. Tangent of 0 is 0. So there you have it. This one, e to the 49 minus 49, right? E to the 0, that's 1. So the last two examples I just wrote up here, these are very easy because the functions we're looking at are continuous at the limit point. You just plug in the value. Now, I would encourage you guys to read, examples on page 64. I have a few more there that are a little bit different. The limit of absolute value x over x is a very common test question, so I make sure you look at that one, 2.3.13. All right. That brings us to the squeeze theorem. What does the squeeze theorem say? All right. So the squeeze theorem says the following. It says if f of x is less than or equal to g of x is less than or equal to h of x, right? For all near a, and if the limit as x goes to a of g of x exists, then, well, let me see, sorry. And if the limit limits of f, g, and h exist as x goes to a, then the limit as x goes to a of f of x is less than or equal to the limit as x goes to a of g of x is less than or equal to the limit as x goes to a of h of x. Actually, to be truthful, I would say that this is the useless form. And I'm jesting a little bit. I say it's the useless form of the squeeze theorem because oftentimes this is not actually the squeeze theorem that we use. This is true, though. What's more interesting is the following, also called the squeeze theorem, which is that if the limit as x goes to a of f of x is equal to the limit as x goes to a of h of x, and f of x is less than or equal to g of x is less than or equal to h of x for x near a, then the limit of g of x as x approaches a is equal to the same thing, whatever this was. So let me call this thing L. Then that's also equal to L. See, because this allows you don't have to assume the existence of the middle function's limit at the point. It's given to you by the fact that the limits of the outside functions exist. So more often than not, when I use the squeeze theorem, I use the second version of it. Show you an example. So I guess this will be ICE 2.4.5. So you want to look at the limit as x goes to 0 of like x to the 4th times the sine of 1 over x. So the trouble with this limit is that as x goes to 0, what happens to 1 over x? It goes to plus infinity from one side, it goes to minus infinity to the other. What happens to sine as you go to plus or minus infinity? Well, it oscillates, right? So the limit of that sine function is not defined, right? However, we can say this. Minus 1 less than or equal to sine 1 over x less than or equal to 1 for x not equal to 0, right? You agree? Sine is bounded by -1 and 1. This is a true thing about sine, we know. And then we can multiply by x to the 4th. So minus x to the 4th is less than or equal to x to the 4th. Sine of 1 over x is less than or equal to x to the 4th for x not equal to 0. Right? Observe that the limit as x goes to 0 of minus x to the 4th is equal to the limit as x goes to 0 of x to the 4th is equal to what? Zero, right? I mean, x to the 4th as x goes to 0, 0 to the 4th, 0. And so, hence, by Squeeze theorem, the limit as x goes to 0 of x to the 4th times the sine of 1 over x is likewise equal to 0. Now, if you look at this problem graphically, it's pretty wild. I mean, what's going on here is you've got x to the 4th, right? And you've got minus x to the 4th down here. And this function, sine of 1 over x times x to the 4th, is this really just wild function that just, what it does is it just oscillates like mad when you get close to the origin. But despite the fact it oscillates like mad close to the origin, the Squeeze theorem allows us to tells us that the answer is 0 because it's pinched down there by its enveloping functions of plus or minus x to the 4th. So Squeeze theorem is sometimes useful if we have indirect information about a function. So that brings us to 2.5, which is continuity of functions, which is where I'll start next time we meet. I'm a little bit behind, my apologies, but I think we'll be back on track soon. And I think, if anything, I've skipped a few proofs that you guys would probably be happy that I've skipped. So sorry I got so caught up in polynomial factoring this semester. It's one of my vices. I love polynomials too much.